Hello, everyone. All right. So last time we were talking about the peak in the photoelectric spectrum for helium. So now let's continue with the trend for carbon, nitrogen, oxygen, fluorine, and neon. So in all these elements, we see a second peak with the same intensity as the peak for the N equals 1 shell, because that makes sense. They have all the 1s electrons, and in each case we get two peaks that are of the same intensity as the peak for the N equals 1 shell, because the 1s and 2s are filled, and then we get a third peak. So that corresponds to the p orbitals. So the intensity of this peak increases as we go from carbon, boron to neon. So we get a single electron for boron, then 6 electrons for neon. So that indicates that all those electrons, they have the same energy. So that's why we only see one peak for the p orbitals. All right. So this reinforces the idea that for the shell model of the atom, but we need to refine the model a little bit to explain the differences in energy for electrons in the N equals 2 shell. So now we have to introduce the concept of subshells within the the principal energy shells or levels of electrons. Okay, so here we go. So if we think about the ionization energies as we go from boron to neon, they steadily increase, and you see those energies are slightly higher than the second peak in the spectrum, which refers to the 2s orbital. And we see that right here going all the way to neon. See that third peak on the right there. It increases dramatically as we go from carbon to neon. So there we go. Okay, so that has to do with the number of p electrons, number of electrons in the p orbitals for neon. Okay, so now that we know the existence of different energy levels within the N equals 2 shell, we can go back to our discussion of different orbitals. Okay, so the data seems to suggest that there's only one subshell in the N equals 1 shell, because there's only one signal. So we call that the 1s subshell. The data also seems to suggest that it can only hold 2 electrons. So that makes sense, because as we'll go into, as we'll see that only 2 electrons can occupy the orbital, because orbitals are also what we call spin paired. So there can only be 2 electrons with opposite spins occupied in an orbital at any given time. The spectra for the third and fourth electrons on the atom are added to a 2s subshell. But however, once we have 4 electrons, that subshell is filled, and we have to add the 5th electron to the 2p orbital. So from this data, we can now construct what we call an atom's electron configuration, going from the lowest energy level to the highest energy level, and that's called the Aufbau principle, filling electron orbitals from lowest energy to highest energy. And we see here, as we go from hydrogen to boron, we sequentially fill up the orbitals going from the lowest to the highest. So we go from the 1s to the 2s to the 2p right here. And by looking at where the element is on the periodic table, we can assign these electron configurations. Okay. So as we continue, however, across the second row of the periodic table, so we go across the second row, we eventually get to magnesium, which goes to, or sodium, that goes to the third row. So now we see here we're going to the 3s, 3p, then 3d, then 4s2. So as we continue across the second row, the number of electrons increases from 6, and then we saw that in the photoelectron spectrum that the neon's signal for the 2p increased, the signal intensity increased dramatically. All right, so now using this data here in the photoelectron spectrum from the spectra data, we could now fill up the electron configurations from sodium to scandium. Okay, so so first let's go over the carbon for neon. We go from the 2p2, 2p all the way to 2p6, and then we can now start filling sodium. Sodium has 4 peaks now, so now in sodium we see 4 peaks. So we see additional peak right here, and that represents the 3s1, a new energy level. So we know it's a new energy level because it has less energy than the 2p6, and we figure out before that when we take the ionization energies, we can't add an additional electron to the second principal energy level because it can only hold up to 8 electrons. Okay. So then we go up to magnesium, a filled 3s2 shell, and then we start going to the 3p sublevel, which is aluminum through argon. And you see here, as we write these configurations, all we're doing is adding an electron into a new set of orbitals until we fill them. Okay. And then once we get past that, we are now going to enter the 4th energy level based on Photoelectron spectrum. And we see here we get, we do see now that we enter the 4th energy level here. Okay, so we see in these spectrums, they by the time we get to potassium and calcium, we find 6 peaks. So it has the 1s, the 2s, the 2p, 3s1, 3s, 3p, and then the next set of orbitals is the 4s. So since we don't see a gradual increase in energy after the 3p, the next logical thing to think about is that it resides in the 4s subshell. Okay. And we see for potassium, calcium, they have now access to the 4th shell. However, when we get to scandium, our model should predict that it should go into a new energy level, right? Because the 4s is now occupied. So now, where should this scandium's 21st electron go? So it has to go into a new subshell. So we would expect, if it went to a new energy level, it'll be higher than the 4s. So it should be at a lower energy than one of the 4s electrons, right? But if we look above here on this chart here, we see that it goes into the 3p, but then it goes into the 4s, right? We assume that it will be the 4s now, but now we would expect the next energy level to be 4p. But remember when I said about with every new shell, there's going to be introduced a new type of orbital. So in this case, we're forgetting about the 3d. So what actually happens is the 4s is actually lower in energy than the 3d, and the next electron is actually higher in energy than the 4s. So it turns out that the 3d comes after the 4s in this case. So when we remove the electron, we're not removing it from the 3d, we remove it from the highest occupied orbital, and that's the 4s. So that's one of those discrepancies that we see here. That even though 3 comes before the 4th energy level, the energy level from the D is so far away from the nucleus because remember that radial function graph I showed everyone? So the less S character your orbital has, the further away it will be from the nucleus. So it'll have no possibility of being approaching the nucleus at a close distance. So it'll be harder for the electron in the d orbital to be close to the nucleus because the orbital is what we call less penetrating. So it doesn't it doesn't like exist near the nucleus, as well as compared to an s orbital. So s orbital is kind of more spherical, looks like the nucleus, so it actually spends more time closer to the nucleus based on its shape. So d orbitals, they're further away from the nucleus than p orbitals, and that's why it's higher in energy. Okay. Okay. So the reason, so it's higher, it's at higher energy than the 4s subshell in scandium. So this suggests that it doesn't go into the 4p because that will be of higher energy, so it should be easier to remove. But in theory, what happens is that it's going to be at higher energy, so it's actually going into a different orbital, which is the 3d, and the 3d is slightly lower in energy. So yeah, when the 4s gets filled, it actually, so it's a weird phenomenon. So why doesn't the 3d fill first for the other elements like calcium and potassium? Well, it turns out once the 4s is filled, it's actually higher in energy than the 3d. So once it gets filled, the ordering changes. So it goes to 3D, then so the ordering is actually 4s and then 3D. So in this case, scandium would fill out the 4s first, then the 3D. Okay. And then it turns out once the electrons are arranged in the 4s, the energies of them switch. So now the 3D is going to fill up, even though it's at higher. It takes a higher amount of energy to remove that electron. So it's kind of a tricky situation there. Okay. So after the 4s, you start filling out the 3D. Okay. So this subshell, we call it the 3D subshell. It's very close in energy to the 4s subshell for scandium, but for scandium, it's easier to remove a 4s electron than a 3D electron. So then we write the configuration as 1s2, 2s2, 2p6, 3p6, 4s2, 3d1, because that's the order it filled. But when removing an electron, we don't remove it from 3D, we remove it from the 4s2 because it's at lower energy. But you can also write this way of writing it is convenient because it follows the arrangement in the periodic table. But if you want to arrange it in the order of ionization energy, it'll be easier to see which electron gets lost first. So we can also write it as 1s2, 2s2, 2p6, 3s2, 3p6, 3d1, then 4s2. Okay? So if we follow this, following scandium is 9 elements, and they're the transition metals. So scandium is not known as a transition metal, just because scandium can pretty much only exist in I think a few oxidation states, whereas these elements, they can exist in multiple oxidation states or charges. Okay, so we have titanium, vanadium, and then zinc. Zinc is at the end of the row. So in this case, there's 5 d orbitals, so it can contain a maximum of 10 electrons in the 3D subshell. So in the n equals 3 level, we can have 18 electrons in that shell. So when we're going around some of these elements here, there's going to be some exceptions. So for chromium, we would expect this configuration, 4s2, 3d4, but the actual configuration is where everything is half filled. So having a half filled D subshell is more stable than having a filled 4s1 orbital, and that's because technically speaking, the electrons in the 3D orbital are of lower energy, so it takes more energy to remove them. So that's why they're more stable. And then for copper, it's better to have a filled 3D subshell rather than 4s because it's, again, of lower energy, technically speaking. Okay? But this arrangement is peculiar because 3D usually comes after. You would think 3D would come before the 4s, but actually it gets filled after. And then once it's filled, the ordering of the energy changes because even though it's filled last, electrons don't get removed from there because once the d orbital is filled, it actually is now lower energy. So it takes more energy to remove them. Okay? So when a positive ion is formed, we say the 4s electrons are easier to remove than the 3D electrons for the first row transition metals. And example of that is, let's take vanadium, right? We remove 2 electrons, we get, we remove the 4s first and not the 3D. So once we remove the 4s, we can actually remove the electrons from the 3D because that'll be the next highest electron orbital where where electrons can be removed. Okay, so those are electron configurations. We'll have more practice with this, not this week, but in a future discussion, probably the week after. The week after the exam, we'll talk more about this. So we'll kind of wrap up our discussion on quantum mechanics there. But so this is where part 1 of chapter 8. We're going to move on to now part 2 of chapter 8 in the next video. So I'll see everyone then.